Number 45. We're given that y prime is equal to x to the negative 2/5 times x minus 3. So we're not told what y is. We're told y prime is equal to this. Okay, and we can say, okay, this is f prime of x here. So let's analyze this. So first off, we're asked for critical points. So this is when the derivative, and let's be clear, the critical points of f, this is when the derivative of f either does not exist or is equal to 0. So I'm going to rewrite x to the negative 2/5 times x to the minus 3 as x minus 3 over x to the 2/5. So we can see that there's two critical points here. One is x is equal to 0. We set x equal to 0, and then we're dividing by 0, so the derivative doesn't exist. And the other critical point is x is equal to 3, because that's when the numerator is equal to 0. So there are two critical points. For part B, intervals where f is increasing or decreasing. Okay, so f of x, we know it is, undefined at I guess I should say f prime. Let me put a prime there. It's undefined at 0. It's equal to 0 at 3. If x is bigger than 3, like 5 minus 3 is positive. 5 to the 2/5 is also positive. It's positive over here. If x is between 0 and 3, like 1 minus 3 is negative. 1 to the 2/5 is positive. Negative over positive is negative. And then finally, if x is negative, if x is less than 0, like minus 1 over minus 3 over minus 1 to the 2/5. So minus 1 to the 2/5 is actually going to end up being positive 1. And so down here, this is also negative. So intervals where f is increasing or decreasing. F is increasing on the interval from 3 to infinity. F is decreasing on the interval from negative infinity to 0, and the interval from 0 to 3. We want to exclude 0 from here because the derivative is not defined at 0. Okay, finally, x values of the local extrema. So we only have one local extreme point, and that is going to be x is equal to 3 is a local. Let's see here, we're decreasing and then we're increasing. It looks like that. X equal to 3 is a local min. Okay, so that's the first three parts done. Okay, now we are going to go on to the second derivative. Okay, so as a reminder, f prime of x is equal to x to the negative 2/5 times x minus 3. So the second derivative here, product rule, this times the derivative of this is x to the negative 2/5 plus x minus 3 times the derivative of x to the negative 2/5 is negative 2/5 times x to the negative 7/5. Okay, so let's see here. How are we going to manipulate this? X to the negative 2/5. Now let me distribute out the multiplication here. X times this would give us negative 2/5. X times x to the negative 7/5 will be x to the negative 2/5. Negative 3 times all of this will give us plus 6/5 x to the negative 7/5. These two terms here, x to the negative 2/5 minus 2/5 x to the negative 2/5 will be 3/5 x to the negative 2/5 plus 6/5 x to the negative 7/5. And so this will be 3/5 times I can pull out a factor of x to the negative 7/5. And so x times x to the negative 7/5 will give us x to the negative 2/5 plus 2. Okay, so here's our second derivative in about as nice a form as we could write it. Once again, we see there's trouble spots at x is equal to 0. We still can't divide by 0. And now, for the numerator equaling 0, x is equal to negative 2. So f double prime of x, negative 2, 0. Okay, so it is 0, negative 2. It's undefined here. If x is, let's see here, x is bigger than 0, positive over positive is positive. If x is between like negative 2 and 0, so like f double prime of negative 1, 3/5 times negative 1 plus 2 over negative 1 to the 7/5, this is going to end up being negative. And then f double prime of like negative 3, if we go down here, be 3/5 times negative 3 plus 2 over negative 1 to the 7/5. And so this is going to end up being positive down here. A negative number raised to the 7/5 power ends up being negative. So intervals of concavity, I guess we did part D, we're on to part E here. So concave up is when the second derivative is positive. So from negative infinity to negative 2, and from 0 to infinity. Concave down when the second derivative is negative, from negative 2 to 0. Okay, so then inflection points, when does the second derivative change sign? It changes sign at negative 2 and at 0. Okay, and then finally, sketch the general shape of the graph here. So the key values we need to worry about are at 0, negative 2, 0 and 3, so negative 2, 0, and 3. Negative 2, 0, and 3. So beyond 3, the function is, let's see here, x equals 3 is a local minimum. Beyond 3, our function is increasing. That's over here, it's concave up, so something like this. Between 0 and 3, our function is decreasing, but it's concave up. So something like this. Concave, yeah, maybe that looks, ignore that, maybe that makes it a little bit prettier picture. How about between negative 2 and 0? Between negative 2 and 0, our function needs to be decreasing, but concave down, so something like this. And then from negative infinity to negative 2, our function needs to be concave up, but decreasing, so something like this. So all through here, it's going to be decreasing, but the concavity changes concave down here, concave up here.